Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the great stuff. This is part of the good stuff. This is the AAS Journal Author Series. And I am very happy to have Bruno Sanchez with us today. Hello, Bruno.
Hi everyone. How are you? How are you doing?
I am doing awesome on this December 9th of 2024 as we record this. And I'm in Phoenix. We are definitely coming into our winter mode. So it will go down, 10 degrees above freezing. Pick your scale, it doesn't really matter. Um, and then we'll warm up to a very pleasant afternoon. And how about you? What's your geolocation, Bruno?
So I'm located in Marseille, France, in the south of France.
Very cool. We're doing international.
So yeah,
Very
no
cool.
snow inside in the weather app, but
Okay.
it's a bit cold. So it's Christmas
Well, yeah,
time.
you have a sweater on, I notice, and I'm still in my winter t-shirt here. So
Yes.
very cool. And Bruno, do you play drums? I see a little drum set there.
Oh yes. I've been doing that since I was 10. So
Oh, very
uh,
cool.
yeah, and since I've been in France, I recently got this ones and helped me get in touch with that again.
Yeah, yeah, very cool. Very, very cool. That's awesome. And Bruno, what do you like to do for research when you're not drumming or riding your bicycle?
So yes, I've been engaged in the transient phenomena research since my PhD. I started working on detecting transients that are related to gravitational waves.
Hmm.
That was my PhD work, and then afterwards I moved to work with Type 1s supernova.
Okay.
So mostly with the uh, dark energy science collaboration, the desk, preparing for LSST for the Vera Rubin Observatory survey.
Yep.
And well, after that, I got engaged in DES and all that, and that's my wheelhouse. I do image to image comparison, the discovery of the transients in different imaging, and then also photometry. So
Very
that's what I
cool.
dedicate
Very cool.
my time.
Very cool. Wheelhouse. I don't hear many people say wheelhouse. That's interesting. And that is going to bring us to this very awesome APJ article. It is open access. It's the open access era, people. You can go grab a copy for free. Go get one. The Dark Energy Survey Supernova Program. Light curves and 5-year data release. And Bruno, take us away.
Great. Okay. So yes, as you can see about this article, there's a lot of people involved. This has been a long time effort by so many people in the dark energy science collaboration. Um, this is a big survey that had paved the way for future stage 4 cosmology surveys, and it has surveyed the southern sky in order to obtain both weak lensing measurements and different performing different probes of the gravitation
Cool.
the model that we have, and then also with Type 1s supernova. And this is what this is about. This is a program that ran since 2013 to 2018, and you can
Yep.
see over here a lot of people in the collaboration. There's people that are involved in DES since the very beginning for working on the telescope itself, the survey of many tools, and also you will see people that are strongly related, and they actually form the supernova working group,
Okay.
which has been doing a lot of effort, a lot of work into putting together this amazing sample of Type 1s supernova up to a very high redshift that it's also able to constrain the cosmological parameters of our universe. So
Mm.
yeah, I would like to mention a few. I worked closely with Dylan Brout, the second author here.
Mm-hmm.
Um,
Yep.
there's been a lot of people also involved, deeply involved in the systems that we use for um, analyzing massive amounts of images from the telescope and producing light curves. Um, um, Also, a lot of the scientific work has been led by people, senior people like Dan Skolnick, Tamara,
Mhm. Uh-huh.
yes, and also yeah, Dan Skolnick, yes, um, And you can see also Tamara Davis, Rick Kessler that's been doing a lot of the framework, Maria
Yes.
Vincenzi also on the systematics, Masao, Sacco. There's a lot of people. I don't want to forget anyone, so I'll stop naming people.
That's a great shout out.
Yeah, it's a lot of work. So
Yeah.
yes, and then yeah.
Very
So
cool.
yeah,
Very
very
good.
proud of the group.
Very good. Quite international group too. Very nice. Okay, and let's go ahead and get into it.
Great. So yeah, this is basically the introduction. It's talking about what we think is one of the most important pros that we have right now for understanding the universe. This is the Type 1a supernova. We use it because these are standardizable candles. These particular explosions enable us to obtain measurements of distance. And this is a very hard thing to do, especially up to that high redshift as we need. So the efforts also in order, yeah, exactly. The efforts of these survey has produced and assembled the largest sample right now of Type 1a supernova that has been observed with a single instrument.
Single instrument, yes.
This is very hard to do. This is very important to reduce systematics.
Yes.
Because in the past, we have been doing cosmology, Type 1a supernova cosmology, by assembling monster catalogs of multiple surveys.
Right. Mm-hmm.
And this is a huge challenge because you need to understand each individual instrument, their selection functions, and any type of calibration quirks and things that you may need. You need to understand perfectly.
Yes.
There's also this redshift range is also super important because it enables you to understand and probe things like dark energy, which is one of the components that we have and we don't understand very well in the universe. So yes, the redshift range is also very hard to do because you need to understand, you need to measure supernova at a very low Z, which is very close by to us, and a high Z. So yeah. So the Dark Energy Survey is a 5-year supernova program. It worked on 10 fields. These are deep drilling fields that you can say, 2 shallow, more shallow, and then 2 more deep fields covering like 27 square degrees. This is
cool. Okay.
the overall look of the survey. So it's from 0.1 to 1.13 in redshift, and we have collected 1,600 more or less Type 1a supernova, which are good for cosmology. And this is a big point, and we will talk about it later.
Yes, very cool.
There was in the first set of papers that were produced for the Dark Energy Survey supernova program. This was the 3-year only spectroscopically confirmed Type 1a supernova sample. This was released in 2019, and we only released at that point 250 light curves.
Yeah.
So one of the biggest challenges with Type 1a supernovae is that you detect these transients, and there are a number of contaminants. So it's very hard to tell whether this is a Type 1a supernova or a Type 2 supernova. And the safest and the most used way of doing this has been always traditionally to take a live spectra of these transients, and then detect some lines like the silicon and absorption lines, and understand whether this is a Type 1a or not. The complication with this is that it involves a huge amount of resources. These are faint objects. You need to integrate in a spectrograph for several hours in order to get decent signal-to-noise ratio. So only 250 were taken up to 2019 of the spec sample. So there was a first cosmological parameter measurement constraint using the sample, but then we are releasing now the 5-year, and this also includes spectroscopically confirmed Type 1a, but we are including also a larger sample of photometrically classified type 1a supernova.
Okay. Okay.
So the first batch of articles with the year 3 analysis enabled us to refining our tools and developing many different analyses that were needed for producing the photometrically classified sample cosmological constraints. These include, for instance, just to name what is in the paper, there are many also tiny tools and developments, but one of the tools is the scene modeling photometry that we are going to talk on this work.
Cool.
Different corrections, chromatic corrections, bias corrections,
Yes.
also correlations with the hosts. This type 1s supernovae explode in different types of galaxies, and this seems to be important. And there are correlations with the hosts that we need to take into account to do cosmology. Also, of course, the photometric classification. This is not so easy to do. It's a very complicated thing to achieve.
Yes.
And then you need to basically orchestrate all this analysis, all these different pieces together in order to produce an end-to-end analysis. So you start from your sample, you apply different corrections, you take into account different correlations, and then to produce the actual result, you need a lot of frameworks that are able to consistently give you the same answer and work your way into obtaining cosmology.
Cool. Very cool. I'm with you.
Yes. So we can go through a bit about what the 5-year analysis then is. So we have, like I said, like 1600 of cosmological grade type 1a supernova, and then the constraints that we obtain are roughly 30% a reduction of the error.
Nice.
In statistical uncertainties.
Yep. Nice.
For the specific parameter of the dark energy equation of state, this is W. And when you compare it to the 3-year analysis, there's a few caveats mentioned here why this is not the naive square root of number of supernovae improvement.
Yes.
There are 3 main points that we mentioned here. One of them is because the spec sample that we also included a spec sample in this 5-year analysis. It was roughly 400, almost 500 of them. So we continue taking spectra of light transients.
Goodness.
So yeah, and this is and specifically for the low redshift events, is basically the same number. The CMB, the cosmic microwave background constraint that we use is very complementary in cosmology for the supernova probe. That was roughly the same. It was very slightly improved. And then finally, the additional events that we include in this sample, because we have a photometric sample now, tend to be lower in SNR.
Yes.
So those are the main reasons why we don't obtain a factor of like you would expect, right?
Just a general square root, right? Cool.
So
I'm with you.
Yes, great. So in the paper is also super important. We are releasing classification scores obtained with Supernova.
Ooh.
This is our main photometric classifier developed by Aix Marseille and Voisier.
Cool.
It's a very complex thing to achieve to be able to commission a classifier that is delivering probabilities that are good for our framework.
Trustworthy.
And then basically in this work, we're going to focus on the photometry and what we have improved with respect to the 3-year and the past releases. So the photometry is a very special point because we depend on it. The Hubble diagram that one uses for constraining cosmology with type 1a supernova, we measure distances in magnitudes, in millimagnitudes. So one can translate very, very simple, in a very simple way, the idea that if you are off in your photometry or in your colors, more importantly, then you're going to be off in your distances.
Yes.
This is it's a crucial step.
Yes.
So there's been more than one technique to do photometry in the past, or let's say more properly, during the survey, you don't have the resources to do a very detailed photometry analysis. You instead rely on the difference imaging photometry, which is on the discovery images of these transients. You use your PSF, your simple model that you can, or your model that you can get of the PSF of the observation, and you do a PSF fitting photometry.
Okay.
And those values are very good, but they are not, most of the time, they are not extracting the maximum out of the, or you can say also, these are not the best fluxes and flux uncertainties that you can get. You can do better.
Okay. Well said. Well said.
So this is SMP for us. This is a forward modeling technique, scene modeling photometry. And this is one of the key points of this paper. And this was run independently after finishing the survey. So yes, this is what we present.
Cool. Very cool. And okay, I'm with you.
Yes. So great. So there are a few caveats to know. SMP is not designed for multi-season light curves. We have a strong assumption that we are dealing with type 1s supernova. So our light curves will last roughly 60 days, and no more than that. And this is a big thing for us. That is also why this SMP is not a general tool that you can apply to any kind of transient and variable.
It's been tuned.
So yeah, this is basically, I think, a good introduction to talk about, like, why this is important to us, what is the dark energy survey, and what are the main points that we're going to discuss.
Cool. Very cool.
So in the figure 1, we have some data. Maybe we can go through that. This is basically showing what a light curve of a type 1s supernova is. So I'll take the chance to briefly mention what we are dealing with. So these are transients. As I said, they last roughly 60 days from the beginning of the explosion to when it really becomes too faint to be detected, and in rest frame. So it can be a bit shorter, but what we have here is different redshifts, different light curves at different redshifts. And in the two types of field that we have a deep field and a shallow field. Okay. And then on the x-axis, this is magnitudes. You can see the 4 filters of DES that we used. We used the GRIZ. And you can see also the phase. So we call it phase because we are working in rest frame, like I said.
Yeah. Okay. And just one question: what do you mean by shallow and deep fields? Yes.
So there are different. The observing strategy that was used for the ES involved 8 shallow fields, quote unquote, which it means that they were visited with less exposure times and less often.
Okay. Good.
And then for the deep fields, we took a few extra observations, and we could co-add these observations together, so we get more depth in our images, and sometimes more exposure time. So the limit, the detectability limit, the sensitivity is a bit higher.
Okay. Cool. Thank you. I'm with you.
Yes. So in the data, this is all properly described in the section that follows after the light curves. These are good examples of them, like what you would roughly find in the sample. So they mentioned, I think in the data section we talk about specifically these fields. They cover roughly, if you add them together, 27 degrees square of the sky. So yeah.
Yes.
Okay. In this first paragraph.
Okay.
During this time, during the time at which we were taking the observations, we were running difference imaging. This is difference imaging is a technique that subtracts directly two images in order to uncover the things that have varied. These are images of the sky, the same portion of the sky taken at different times. So when you obtain this difference, you do it pixel by pixel. You have to take into account many parameters that are, observing conditions, and then like the PSF, the brightness of the sky, and so on. So you can equalize the photometric properties of these images. And then when you subtract them, you find that the bright pixels that were left behind are where these transients are. And then you can also perform photometry on these images. The 2015 Kessler paper basically describes what kind of pipeline we have been working on in the ES with in order to discover our transients. And this is characterizing this pipeline is essential for us to understand our selection function and how deep we can go, and so on and so forth.
Yes.
More, even more, this technique is not super clean. It can produce artifacts. The images can have different, defects. It can be defects of straight light. You can have saturation. You can have many problems that also can be detected as transients, and you need to remove them. This is also the Goldstein paper where you can classify them.
Cool.
And then once you have obtained more or less a reliable transient that you think it's a valid SN1A, you need to follow up and obtain spectra of their host. Why? This is essential to the cosmology probe. We need redshifts. So this has been produced by the AA omega spectrograph in Australia. This is part of the AAS survey, which provided us with, most of the redshifts used in this sample. So there is a big contribution.
Very good. Shout out to OSDES there. Very cool. Okay.
So after you have your candidates and your redshifts and all that, you need to do photometry and you need to calibrate this. So the dark energy survey itself needs to do this either for transients, but also for galaxies, for any type of measurement that they want to do. So there's the FGCM is the forward global calibration method. This has been developed by Rykov and Burki and others. And in this main technique, you basically obtain through tertiary stars in the sky, you obtain a basic calibration, and then you can tie it. You can tie it to a standard like an HST CASPEC standard. So we use it for images. It's briefly described over there. What has been the changes between the initial FGCM and then the final FGCM sample to use for calibration, which is the DES 6-year data set. So these improvements also, we could include them now in the 5-year, but were not available at the 3-year sample. So this is also an improvement for us. And there's a summarization over there. We can go through this. Basically, we have corrections to the aperture photometry used for the stars that we use for calibration. There were updates to the band passes that we can characterize for DES. Better uniformity across the, there was some bad weather. You can always you can always improve on that. You have to deal with that. So there are improvements that happen because of you can take another year of data and get better.
So here we go.
There's also a key aspect, which is some stars would move because they are very close by to us, and you can detect that. So the astrometry, you have longer temporal baseline. You can improve the astrometry and account for proper motion of the stars, and then refine the measurements, the repeatability of their magnitudes. So that was also naturally included in the latest catalogs. And
beautiful.
And then that is like a general calibration that we need for the survey. But then type 1A supernova cosmology analysis need to patch different surveys together. In the past, we did it because we didn't have a single survey that could cover all the
Gotta
sky
use
and
it.
all
Yeah.
that.
Mm-hmm.
But we still need a low redshift sample, and this is important for us in order to be able to tie the distances and obtain a wide range of redshifts to constrain dark energy and the acceleration of the expansion of the universe. So why I say this, because we need to do inter-survey calibration, and we do this with supercalfragilistic method from Brout 2022.
Mm-hmm. Mm-hmm.
So we use this technique. This technique is putting together the different surveys, their filters, the transmissions, and then using a common catalog to obtain a global solution in the offsets of their filters. So we use this calibration and then also compare to the ones found by Rykov, and we're more or less consistent. And we chose to keep working with these with our own determination, because we can have them naturally in the previously used supercalfragilistic system that was used for different works.
Yes.
We also can derive covariance between the filters that we have in our DECAM in the DES camera, and also the filters of the low C sample.
Yes.
And this is super important for us. And then it allows you, once you have this determination of the system, it allows you to simulate and provide simulations of your supernova magnitudes, and it's important for our corrections of any bias. So
very cool.
Yeah, this table summarizes a bit differences in the technique.
Okay.
Oh, I think I can show them later. Sorry.
Okay.
Yes. But basically, this is the calibration. Then, as you can see in the final paragraph, we cite the work that determine the offset to the CalSpec standard. This is the HST C26202, and we show over there that we have an understanding of our system to a few millimagnitudes, which is what you need.
Super cool. Okay. Nice. Okay.
So far, so good. Any questions?
I am good so far. I am following you just fine.
Great. So then we're gonna talk about the different techniques that we use for photometry.
Okay.
So there's this forced PSF photometry on the difference imaging results, the IA images, which as I mentioned, are a pixel by pixel comparison between old images and recently taken images. You use them to detect transients, but also you can use them for photometry. And so in order to obtain the subtraction, you need a template image. So this means that you would take your survey archive of images and perform a coaddition of these images to obtain a very deep template, we call it. Okay. So this is the best, the best representation that you can have of the static sky. Since we are dealing in transients, you can have your cloud image that has all the galaxies and stars. It averages out, and it's deeper. And then when you run your subtraction, you have a very good model of the sky, data-driven model.
Cool.
Then this is how you basically detect the transients, and you can do photometry on those. This is general solution. This is able to detect any kind of transient or even variable stars, and it's not optimized for any kind of photometry of type 1a supernova, very deep, or transients like us. Then there's a way that we do a calibration. We use different tertiary stars in the field to obtain a photometric calibration in difference imaging, and then that's how we obtain our magnitudes. Then we have the scene modeling photometry.
Yes. Okay.
The scene modeling photometry is the alternative, the more precise technique. It's also very demanding in resources, so it's not something that you want to run
all the time.
Periodically. Yeah, you do it after you gather your data and you have a rough idea of where the transients are. So in this work,
Nice.
we have processed almost 32,000 candidates.
Nice.
In the year 3 paper, which is mentioned over there in the 2019 year 3, we processed 250 of these, and
Okay.
this time we run all the transients
Okay.
that we have collected, and this is what we present in the release. So we obtain light curves for all of these objects.
Cool.
Some of them will not look like a transient and would be, like I mentioned, like AGNs or different types of periodic variables. And in that case, SMP is not doing a great job because it's assuming that it's transient-like. So that's why we obtained successful SMP fitted light curves for 19,000.
Very cool. Okay. Okay. Very cool.
Yeah.
I'm with you.
So the way this works, I think we could probably go to the table. It will be good because we can have a comparison between these two techniques.
Let's take a look at this. Okay, let's blow that up a little bit. Maybe not.
Great.
There we go. Okay.
So this is highlighting what are the differences between the difference imaging pipeline and its stages and the SMP. So what we call template is what I talked about, like having a deep archival coated image of the sky in order to be able to subtract the static sky.
Yes.
We use science verification images in difference imaging, and then in SMP we have available the entire archive for us to do. This is the first line of the table.
I'm with you.
Any high quality images that we have taken before or after the transient can be included. Then the 0 points are used are obtained using the latest catalog in SMP year 5, while as in the real-time survey we were not able to do that.
Yeah.
The photometry is done in a consistent way in SMP, whereas in the difference imaging we were using apertures. Yeah, the magnitudes obtained by apertures that were changed according to the PSF in order to account for atmospheric turbulence. So it clearly changed. Then there's like no accounting for the proper motion of the stars that we use for calibration, whereas we use a linear fit in the year 5.
Yes, better than none.
The science verification. In the astrometry as well, we got improved astrometry. The position of the transient was basically an average in difference imaging, but instead in SMP we could fit a model of the position that is per filter. So it's common across all epochs, but per filter. So that allows us to obtain a very accurate position. The host galaxy, we were using again images, the template images, and we forward model it in SMP. And then finally, the flux measurements, which is something that it would be nice to discuss further, is how we really obtain the fluxes. So this is probably better described in the Broad paper that introduces the technique, the 2019 paper cited. But basically what we do is a forward modeling of the full observation, the image where the supernova shows up.
Okay.
So what we do is each time that we have observed that image, we have observing conditions, properties like the PSF, the noise of the sky. We have the photometric properties using the stars and all that. It gives us a possibility to forward model an image that we cannot see. This is a true image, a true scene. It's an underlying model.
Right.
This would be the equivalent of taking an image with a perfect instrument in space, probably an infinite aperture telescope.
Nice.
Right? That would be nice. And so where our PSFs are like delta functions.
So it's been,
And then what we model is basically all the degradation that an image will have when it goes through our system. And that's what SMP is doing, is forward modeling completely the observation. And then we do PSF photometry. We obtain the flux measurement from this modeling. And we do this in using Markov chain Monte Carlo with every image that has observed the supernova. And then for the galaxy, for the host galaxy, which is in the background, and you want to deblend the fluxes between the galaxy and the supernova, which is on top, you take into account the highest quality images that you have, either before or after the transient has faded away. So it's a very precise method.
Very cool. Overall, some very significant improvements in Y5.
Yes. So we can scroll down. I think this technique it's also able to obtain the uncertainties of the measurements. So there's a lot of technical discussion over there. How you in the left side how you choose your images to for the templates for the host galaxy, and how you really process the data. But again, it's basically summarized in the table. I think there are probably a few important quoted numbers, like the improved astrometry. We are able to in the end fit the positions of our transients within fractions of arc seconds. So it's really very cool. It's performing very well.
Very cool.
On the uncertainties, I think this is also super important because that's where we talk about the offsets in astrometry. In the 2.5 subsection, we discuss the uncertainties. So the difference imaging pipeline, when you do forced PSF photometry, you would determine your errors as you would do the PSF fit procedure. Is pretty straightforward. But we on SMP work with Markov chain Monte Carlo to determine the full parameter configuration of the host, of the supernova, the position, the flux over time, and our uncertainties are determined using the variance of our chains. You can see this is the SMP, sigma SMP, and then we can include shot noise from the actual supernova and shot noise from the galaxy.
Poisson shot noise. Oh yeah, here we go.
So that is the full variance, and then these uncertainty also we would co-add or combine measurements and uncertainties obtained during a single night. We can have more than one image per night. So in the Likert fitting procedure during the cosmology analysis, you don't want that. It's not super useful to have more than one observation per night. You instead prefer to have one with the highest SNR.
Yes.
That's better, and we do it by doing a variance weighted average, which is described over there. It's pretty straightforward, but that's what we do.
Okay.
That is a variance of the flux, but then there's also a correction for an effect that I think as a community we yet have to understand, and we will see in the future surveys if we detect the same. But this is called the surface brightness anomaly.
Okay.
Oh, let me turn the light.
Here we go.
The lights. Yeah. So this is a systematic underestimation of your uncertainties.
Okay. Yeah.
So you can know, yes, and it's related to how bright is the host galaxy. So it is basically telling you that in brighter environments, when you determine your fluxes, you underestimate your errors. And in difference imaging in the difference imaging pipeline, we found an effect that it was bigger than SMP, and this is discussed later on. Any deviations from that, any underestimation of the uncertainties, we have to correct for, and so we use that as a map, as a table that we use to correct a lookup table for our final uncertainties. So anything that I described before will be scaled up by a factor that is determined using the host surface brightness for each individual supernova.
Okay, I'm with you.
So yeah, we're gonna probably there's a figure about that that we can see. I don't know if it's figure 3. You can
go there now.
Yeah.
Let's go to figure 3. Okay.
Right.
Okay.
So this is what I'm talking about in the host surface brightness, the x-axis. You can see this is magnitudes per arc second square. So this is how bright is your host galaxy at the position of the supernova.
Yes.
Right at the position of the supernova. If in order to collect this information, you have to either have prior images of the host where you can do photometry on the location of the transient.
Yes.
Or you wait after and you do the measurement. So the main idea is the galaxies, the host galaxies, will have different distributions of these host surface brightness in different band passes. So this is where you see G, R, I, and Z.
G, R, I, and Z.
Yes. You can see the distribution of the host's brightness, and then you see a progression, which is the RMS. This is basically measured when the supernova flux would not be detectable anymore.
Yes.
So this is either like, I don't remember exactly, by like 30 days before peak or something like 90 days after peak.
After, thereabouts.
So you perform SMP measurements and difference imaging PSF fitting measurement of the flux at the location of the supernova at those times. And they should be 0. So you can estimate with the uncertainties an RMS of this ratio, the delta flux that you actually measure with the uncertainties. And if your uncertainties are well measured, it should be 1.
Cool.
It should be a Gaussian. It should look like a Gaussian distribution centered about, in 0 and with a dispersion of 1. And it's not what we see. And if you take all these measurements, these RMS, order them by surface brightness of their host, this is when you construct this curve.
I get it.
And in difference imaging, you can see it's a bit higher, and in SMP, we recover less of that. And it depends on the filter. So it's not super trivial, but it really depends on that.
Yeah,
you can see that in R, we improved significantly, and in I as well.
Definitely.
In G and Z, it's not so obvious, but we are overall better with that.
Mix on G and Z, but definitely some improvements in R and I. Okay.
We still see it though, and it will be interesting if we could understand in future surveys, or if we could really have an explanation for that, a clear explanation that why we have underestimation of our uncertainties.
Yes.
But in the meantime, we correct for it. I think if you go up, there's an equation that basically shows, equation number 2. It's basically.
All right, I missed that. Okay.
Yeah, there's a figure in between. But equation number 2 is basically the final flux uncertainty. We scale the uncertainties by these S. This is basically following the curve that we measure. And this is the final errors that we have in our photometry.
Okay, I'm with you.
Yes. So this is the flux and the uncertainty measurements. Then there are some corrections that we have applied, and we have, the Supernova working group members have worked very hard on many different correlations and corrections, and one of them is the DCR. This is a wavelength dependent correction that is due to the atmosphere. The atmosphere doesn't behave, the same for every wavelength. And so if you have an observation right at the zenith, you wouldn't have any difference for any wavelength. But as soon as you're not observing on the zenith, you see refraction that will be different in different colors.
Yes.
And this is what we call differential chromatic refraction. And it can change many things. It can the first thing that you would learn if you look at this effect is that it will move your objects. It would move your blue objects different than your red objects. Supernova are very blue. So it's a very important effect for supernova. And even more if you observe them at lower altitude or higher air mass, which is the key parameter here. It will move. It will move even further. Not only that, it will also change the PSF and it will also obtain biases in your photometry. So we have characterized that. The changes, you can see it's up to 3 millimags. This is the Lee and Acevedo paper 2023. And we provide in the release a table where you can basically apply a correction of VCR to the objects independently. The corrections are not included in SMP straightforwardly because we were developing this independently. This is one of the, if you have infinite time, probably you could have done it, but we didn't. So yeah.
Yeah, infinite time is nice.
Yes, but impossible. So
okay.
So that's basically encompassing, it encompasses all this description, the main differences between SMP and difference imaging, and what you have to do to get from your images all the way to get enough flags and an uncertainty of the flags that is useful for cosmology.
Yes, that was a great walkthrough on that stuff.
Yeah, great. So we performed some comparisons just to see how it compares to the difference imaging real time photometry and SMP. We have done that, and we obviously see a great deal of improvement. There's many things that you can test. One of them is when you fit. Sorry, let me start by saying this. When you perform type 1a supernova cosmology inference, you need to fit the lie curves to a model. This model, which is SOL3 model at the time, is a basically SCD time series model, a spectrophotometric time series model of the type 1a supernova that can be fed. So you can basically obtain a lie curve fit that gives you in a few parameters that are used for the distances as well. They're lie curve properties. And presumably, if your observations are bad, then your fit is not going to be so perfect.
Yes, hopefully.
And if your measurements are better, then you would see a reduction on the basically residuals of your fit. And this is what figure 4 showing.
Let's go to figure 4.
So it's basically looking at the dispersion of the observations minus the model predicted brightnesses of the supernovae. And we are ordering our data in redshift. So you can sort of see, and also redshift would correlate with many things. The supernova spectral time series moves to the red. You will see, how the G filter kind of cuts off. And the remaining filters up to Z, you still have enough events, and also redshift correlates with the SNR. You higher redshift, your supernova will be fainter. So we were comparing with difference imaging photometry, how was the residuals, and we are doing better overall. Or if difference imaging analysis photometry was good, we're performing similarly to that.
Good.
So this is one way of not relying on simulations, but using the data to fact check our photometry.
Very cool. Very good.
That
looks good. Okay.
Yes. So
Reasonable.
then there's a straightforward comparison. It's in figure 2 actually,
Okay.
with the previous S&P run, the year 3 release. In
Ew.
the year 3 release, we obtained S&P light curves for only 250 events. That's why this
Yeah.
diagram shows only so many of them.
Right.
And we are straightforwardly showing you the difference in magnitude. This is showing that things agree when the signal to noise ratio is high.
Okay.
And then we are also seeing that we can, the way the progression ends, which is on the negative side, tells us that
Yeah.
S&P year 5 is a bit more sensitive.
Yeah.
So
Mm-hmm.
every time that things are cutting off, it's because the S&P year 5 magnitudes are better estimated,
Right.
and also stats are low at that so the
Uh,
conclusions can be limited, but in any
bingo.
case,
Okay.
we can see across many magnitudes, this is a wide range of magnitude between 20 and 25 almost. You can see that these things are providing similar answers for magnitudes.
Yeah.
There's also a full micro chain Monte Carlo happening in year 5, and many improvements that we had talked about already in
Yes.
year 5 that we didn't have in year 3. So the differences are expected, and they are fine.
Uh-huh. Very cool. Beautiful comparison. Nice. Okay. Cool.
So yeah, so I think this is a lot of work compressed into into a few figures,
Indeed.
um, but we can describe in this table. Yeah, it would be nice to talk about this.
Yeah.
So given that we are using so for S&P, as I said many times, we use images before the explosion or after the explosion
Yes.
to constrain the host properties, the brightness of the galaxy host.
Yes.
In order, when you do that, anything like an AGN or a variable star that would have contamination plugs in those images from the transient, because it wasn't a supernova,
Right.
you might have a poor fit with S&P, or even the chains will not converge. So,
Okay.
and then S&P is performing this chain for each filter individually. So
I get it.
each filter can fail individually as well. So in this table, what I'm showing you is that the difference imaging light curves, we started with 30K of our transients,
Yep.
and that's what you get. You can perform photometry on them with this technique. With S&P, you can't. You only can achieve photometry for roughly 19,000.
Yes. Okay.
And the number of filters that you can have in your light curve can be 4 if all of them achieved fit, or it can be any 3 of them if one of them failed, and so on and so forth.
Right. Let's see.
So yeah, and
Okay.
then what's on the right in that table, it's talking about different quality cuts that we impose to our sample
Yes.
in order to use them for cosmology. This is
Mhm.
just a few of them. There are many more. I would encourage the people who are interested in looking into the Vincenzi's paper, which is fully describing all the analysis,
And
or in the cosmology paper.
we will put a link to that paper below the video as well. So, okay.
Yeah, great. But the multi-season cut is basically asking the data, do we have signal in one or more in more than 1 year of observations? If that is true, this might not be a supernova. So you cut your sample.
True.
So
Okay.
then you're left with 14,000 and 13,500.
Okay.
So right now you can see straightforwardly that the S&P light curves that we are failing to fit had an issue going with that.
Right.
the,
Right.
the multi-season. Then
Right.
the probability over there of being a type 1a, this is coming from our photometric classifier Supernova
Yes.
from Moller. And you can see that we are also shaving 2/3 of the sample, roughly.
Right.
we haven't yet been consistent between the two samples. But then if you ask how many of them have a successful type 1M model fit, Sol3 fit, and then also have host redshift,
Yes.
you're left with 4,000, 3,600. And finally, including all the cuts that are not in this paper, but are in the cosmology and systematics paper, you can see how many of them end up being in the Hubble diagram. So how many of them are cosmology grade? And you can see that S&P has a few more. So this means that, you know, even if it looks like we might be losing supernova, the quality of the ones that go through our pipeline, S&P, are very good. And we are actually rescuing a few of the ones that we couldn't with difference imaging photometry.
Right. So it's a standard of sorts. So
all this effort pays off in a few of them, but they are valuable. So yeah.
Yeah, very good. So you get about from 19,000 to 1635. It's about a 10% yield on the high quality, roughly.
Yes. Yes. There's also a few in the text. I don't remember exactly where, but this matches predictions before the survey where we were looking into how many of the transients detected are going to be type 1a supernova. Yeah.
Yeah.
Yeah. Okay. So yeah, this table is nice because it shows us that S&P is useful and it yields more supernova. And then, you know, I think what we remain to discuss is basically how do we obtain some of the information that's present in the release. We're releasing not only the light curves, we're also releasing, you know, a big amount of data.
Redshifts, those galaxies.
Yeah. For instance, redshifts of the supernova that were obtained with the AAS, host galaxies properties. These are essential properties for doing cosmology because you need to know the mass of the hosts and also their colors. So that's why we use different SDSS and VSTAT data, also different codes to perform this photometry. This is all very detailed work that needs to happen. Then for the low redshift sample, we included, so in previous cosmology, type 1a cosmology samples like Pantheon and so on, Pantheon Plus, they were using many low C, especially also for any Hubble constant determination. You need to use as many supernova at low redshift as you can get, and you can calibrate. But we made different choices in DES. We chose to use the redshifts and the supernova from different surveys that we could rely more. We believed that they were easier to model, their selection function, and we could include them in this analysis. So you can go and find out about them more, again, in the cosmology paper or in the systematics paper, but basically their redshifts came from there. And also their host properties, how we obtain consistent information between the high Z and the low Z. For the hosts is also a significant amount of work that need to happen.
Yes, indeed, especially if they remeasure all that.
We need to remeasure many of the properties in order to be consistent, as I say. So in the conclusions, I think we're right now in the conclusions. It's basically a super large amount of work. It's a collection of many different tiny and big contributions, piecing together in order to obtain this largest collection of transient light curves, and also the largest collection, of cosmology grade type 1a supernova in that range. That is also from a single instrument. So
beautiful.
So all this work amounted to a long list of improvements. We could have, you know, in the cosmology paper, in the final Hubble diagram, we have like 1800 type 1a supernova. This is one of the first times we achieved that. And the redshift distribution is also higher redshift. So this sample is particularly deep. And I think it's worth also a read how this was used for the cosmology and what we obtained from that. So that's also listed here because this paper is the release, but it leads to those, I think. And then we have learned. I think this paper also is showing that for future surveys, like the Vera Rubin LSST, which I work with,
yes,
and Roman, for instance, there's many things also to work and develop to have this type of photometry, super precise photometry for these surveys. So yeah, that's roughly the paper. I think it's also important to know that this work has a few appendix that
important
show yes
how to actually, let's go down to that, how to actually get it. There's the GitHub and on Zenodo.
Yes, we have released. So we have provided the photometry. We are actually we got accepted the paper like a few weeks ago, and we haven't released the difference imaging photometry for the 30K. It's a big file, so we did not. Also, it wasn't used for cosmology.
Right.
And we released the cosmology grade light curves and all that from SMP, and the difference imaging is going to come out in a different Zenodo. That is the only caveat.
We look forward to that. Okay.
Yeah, we're doing that now. Now that the paper is accepted, and there is a list of what we provide with that. If you also go to the GitHub, we have put in the effort to create a web page where we have a full description of the data release of the files, examples of them, and also tutorial Jupyter notebooks for people who want to use them for teaching and loading up the data straightforwardly. We've included utilities for working with Python, this programming language that is very popular these days.
Nice.
So you can load up a light curve like this one that you can see with the fluxes and all the parameters. For all the samples straightforwardly, and this is, I think, also a valuable asset.
Very cool.
So yeah, I think this summarizes the release, I think.
Beautiful.
So I really encourage people to go visit the website. If you use the data, cite this paper, cite the cosmology paper.
Yes.
And
absolutely beautiful, 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 beautiful. Bruno, I want to thank you so much for walking us through this very awesome data release article. Very cool.
Thank you. Thanks for the invitation. I really had a good time.
Sure. And you kind of touched on it. Oh, you're definitely in France because the sun's going down. It's darker than when we started.
I turned out my light. Yeah.
Excuse me. So you kind of touched on it a little bit there, and let me go ahead and push on a little bit on where do you think we go from here, given the published article? Is there an anticipation of a year 7 data release, a year 10 data release? Is there more stuff in between to maybe take care of in the more short term? So just sort of next steps. Where do you think we go from here, given the published article?
Yeah, so it's a good question. It's a very good question. I think so. The Dark Energy Survey and the Supernova program run from 2013 to 2018, and there's no more data taken.
Okay.
Yeah, so this is, you could say that this is the final data release for this experiment.
Yes.
There's been the central cosmology paper where we test the traditional, let's say traditional, or the standard model than the CDM, but there are also articles that are coming out that have tested alternatives to this model, different exotic cosmologies. Work from Ryan Camilleri and Tamara Davies. There's also work done by Phil Weisman and people in the UK about some of very interesting transients that are in this sample that we haven't used for cosmology. There's a lot of data that we haven't used because it's not a type 1a, but it's also a very interesting object sometimes.
Cool.
And I think also the community is looking at the cosmology that we obtain with this sample, in combination as well with DESI. And there's I think a big debate these days, because we might have a slight hint of evidence for a dynamic dark energy scenario where W is not a constant. And
Right.
I think this sample, this release, is going to be used by hopefully by a lot of people in the community to really test this even further.
Yes.
And to produce constraints on different types of cosmological models that we haven't tested. And that's basically what I see for this article. But then for the type 1a supernova, I would love to say, if I may. So I work with the Vera Rubin Observatory, and this is going to be one very exciting time in the next few years for type 1a cosmology. We're going to collect so many of these. So
I'd also be happy to know what the progenitors of type 1a are. So yeah.
yeah. We're using this standardizable candles, but we sometimes don't understand fully.
We don't actually know what it is that is exploding. Yeah. So both those would be really cool. Well, listen, I agree with you. This is going to be very exciting over the next couple of years to see this, the fruits of this catalog come out and on the future ones with Rubin. So it'll be really cool. It'll be really nice to see.
Yes, I agree.
All righty. That will do, everyone. Bruno, thank you so much once again.
Thank you. Thanks to you.
Yep, and that will do. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.